Okay, so now we know the kind of the high-level concept of how Dijkstra's algorithm works, right? At each algorithm step, it adds a node to a tree, and the property that it uses to select that node is it says I want to make sure that that adding this node to the tree adds a new shortest path to my list of shortest paths. Okay, so the obvious place to start here is just to initialize the tree with the node A. So here what I'll do is I'll select the node A and I'll color it this pinkish red color. And that will mean, as we go through this algorithm, that will mean that is the tree, the current state of the tree. So what we do is we look at the tree, we look at all the nodes that are adjacent to the tree, and then we add one that increases the length of a shortest path by the least amount possible. Okay, so what we could do is we could kind of figure out a way to frame the current state of the tree as a list of shortest paths, and then we can go from there to figure out what node to add next. Okay, so oops, I want to keep that red. What shortest paths is this initialized tree expressing? Well, you could think of this as the shortest path. It's the list of all shortest paths to A from A. Okay, so shortest path from A to A. Right, so it's the trivial shortest path from A to A, right? Just stay where you are. Don't go anywhere. Okay, so what we do in Dijkstra's algorithm is we look at each node that's adjacent to the tree, right? So these two, right? Those are the only two nodes that are adjacent to the tree. And the easiest way to think about this in step one is we just add the one that has the smallest edge weight connecting it, right? If it's adjacent to the tree, then we know that it is adjacent to some shortest path. And so if we add, in this particular case, in this case alone, we add the one that has the shortest, that has the smallest cost, then we know we're adding a shortest path. So what do we do in the next step? Well, we add node C to the tree. So what I'll do is I'll select this. I'll copy it down below. And I will add node C. Okay. So what we're doing is we're scooting this down a little bit, get rid of my arrows, and I will include now node C. Okay. And so now in step two, node C is added to the tree. So now how did we decide to do this? Well, we said, hey, look, my tree is A, my adjacent nodes are B and C, okay? And the distances from B and C to A are 2 and 1. So what I'll do is I'll pick the one that has the shorter distance. Okay? So at each step, we're going to look at the nodes that are adjacent to the tree and then add the one that is closest to A. Okay? Not necessarily add the one that is closest to the tree. In fact, in most cases, it won't be the one that's closest to the tree, but we'll add the one that's closest to A via the tree. The fact that A is part of the tree means that we're guaranteed that the one we add, once it's added, will have a path that's defined to A, because then once it's added, it's part of this tree. The tree is defined as the list of all shortest paths to A. And this fact that we have optimal substructure in this problem means that it is connected to an already shortest path. Okay? So let's see how this kind of plays out as we go forward. Okay, so now after step one, now we have a tree that's a little bit more interesting. And so now this ends up being slightly more interesting. So we've got the tree that looks like this. The tree is the nodes A and C. And so what we'll do is we'll say what nodes are adjacent to the tree. Well, the nodes that are adjacent to the tree are B and E. Okay, so what is our tree? Our tree is A and C. What nodes are adjacent? Well, B and E. And then we can ask, what is the distance from those nodes to A? Well, to do this, we have to record the distance from every node in the tree to A. Okay, so what's the distance from C to A? Well, it's 1. So then what's the distance from E to A? Well, it's the distance from E to the tree plus the distance from wherever E connects to the tree to A. Okay, so the distance from E to A is 3 plus 1, which is 4, and the distance from B to A is 2. Okay, and so what are we going to do? We're going to add B to the tree. Why are we going to add B to the tree? Well, because B is the one that increases the minimum path distance to A the least. Okay, so in our next step, we're going to add B to the tree. All right, so I'll select B here and add it to the tree. All right, and then we can get rid of these arrows, and we can do this. Okay. All right. So why have we added B? Well, because we know that wherever B connects to the tree, it's connecting to a shortest path, and we know that that means that the shortest path from B to A must be just the edge that connects it to the tree, and then the following shortest path from there. Why is it the case that there can't be a different path from B to A that has a lower distance? Well, we know that the tree is building up this list of shortest paths, and so there must be one more shortest path out there somewhere that connects to one of these already known shortest paths, and it turns out that the one that connects has to be one of these nodes that's adjacent to the tree. So the one that extends the kind of the shortest path from A the least has to be correct. Okay, and so one of the questions is why is it guaranteed or why isn't it guaranteed that connecting E to the tree at that step was going to give us a shortest path? Well, in some sense, we hadn't explored this yet. We hadn't explored this edge yet. Okay, so in the previous step, let's look back at the previous step. The previous step says we're considering adding B through this edge or adding E through this edge. If we add E through this edge, then it says the shortest path from E to A has a length of 4. So the question is, why did we choose? Why couldn't we choose E? Why couldn't we add E to the tree at this stage? And the issue is that we didn't know yet that this was a 5, right? For all we knew, this number here was, say, a 1. Okay, and so we know that adding B to the tree increases the shortest path, by the least amount, and thus B has to be the right one to add. But we have no way of knowing yet that that the shortest path from E to A connects to the tree there. It might connect to the tree somewhere else once we've built the tree up a little bit more. Okay, so that was a 5 right there. All right, moving on, let's go ahead and finish out the algorithm. So moving on, what do we have? Well, now our tree is A, B, and C. Oh, and then as we go, we'll record on the node the shortest path, the distance of the shortest path from that node to the tree. All right, so our tree is A, B, and C. Then our adjacent nodes are D and E, right? So we're considering this one and we're considering this one. Okay, so D and E. What are the distances from D and E to A? Well, we already know that the distance from E to A is the distance from E to the tree plus the distance from that node on the tree to A. So the distance from E to A is 4, right? 3 plus 1 is 4. And the distance from B to A is this number, right? It's 2 plus the distance, the ongoing distance to the tree. So the distance from D to A is 4. And this is essentially a list of the shortest so far known distances from these nodes to A. And so now it doesn't really matter which one we add next. We can break ties alphabetically and say let's just add this one. But there's a tie, see, in the shortest distance from those nodes to A, so we can add either one we want. So just for the sake of having something to add, let's pick D. We'll suppose we're breaking ties alphabetically. So we'll add D to the tree. Okay, so once we add D to the tree, we'll add that in there, and we'll write the cost of the shortest path from D to A, right there on D. So the path from D to A is of length 4. And then we can let the algorithm proceed. So now we can say what is our tree? Well, the tree is A, B, C, D. What are our adjacent nodes? Adjacent nodes are E and F. Or F and E here, and I'll write those in a list like I've done before. So E and F. So the shortest known distance from E to A is still 4, right? Nothing has changed there. It still connects to the tree at, via C. And now the shortest known distance from F to A is 5, right? It's 1 plus 4. All right, 1 plus the distance from D to A. Okay, so here now this is 4, this is 5. So our next step is going to be to add E, because it's the one that increases the shortest path by the least. So we add E into the tree. Copy. Okay, so our next plan is to add E. We have to be careful about which edge we add with E, right? We don't just add all the edges that E gives us. We add specifically the edge that E was connected to the tree by to find its shortest path. So, E was connected through C, right? So E is connected to A through C, and so then the edge from E to C is the path that is the edge that we include in our tree. And so now we have almost everything left in our tree. So A, B, C, D, E is in the tree, and the only adjacent node is F. And so the only thing we have left to do for F is to determine what its shortest path is to A. So what's the shortest path from E to A? Well, it's 4. So F can either connect to A through E, which would give it a shortest path of 6, or it could connect to A through D, which would give it a shortest path of 5. Okay, so the one that it connects to A through is D, right? That's the smallest, and so what we have in the end is our final tree. Our final tree adds that edge, and that's what we have. Okay, so here's the algorithm output. Algo output, right? The spanning tree that contains all shortest paths, and we can essentially just delete those two. All right, so there's our list of shortest paths in the original graph. Okay. And notice this isn't the same thing as what the DFS kind of inspired algorithm gave us, because this one was smart, and it kind of built up the path lengths, iteratively as it moved out.